Welcome to today's webinar. The topic today is stress analysis of stair models in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and PR in the Dlubal Software company. For instance, the website, the webinars, customer projects, newsletters, and so on. I will be the moderator today, and I will answer your questions together with Lukas. But yeah, my two colleagues can introduce themselves.
Okay, thank you, Andreas. Then I'm Andreas Niemeyer. I'm responsible for the product engineering here by Dlubal. I take care which wishes we transform into features, in which way of concept we are doing this, and I plan this with our programming team.
Yeah, hello also from my side. My name is Lukas. I'm hired here as customer support and product engineer, usually with the focus on the interfaces. Today, however, I will support Andreas in the chat.
Okay, thank you for your introduction. Then we can switch off our webcams so the attendees can see the full screen. I say something, at least for the attendees who participate the first time, how you can ask questions. You can ask questions with the control panel that you can see on the right side of your screen. You can show that with that arrow here, and then you can enter your question here, and we will answer you. If you don't get an answer during the webinar because there are too many, yeah, you will get an email after the webinar. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's also all from my side. I hand over the screen to Andreas. Andreas, it's your turn.
Thank you, Andreas. Then I take over with the webinar about stairways. Today I captured, let's say, some features in our program to show you how you can use our stress-strain analysis program by adapting it or by using it on stairway models. Of course, I invest some time to show you how you can create such a stairway model, how you can apply loads, how you can analyze results, and how you can document it. As example, I have here on my slide some pictures what should give you an impression what we want to do in the next hour. My plan is that I lead you through the modeling and design process of such a spiral staircase, what is consisting of some, let's say, prefabricated stair steps. What you see in the second picture, these stair steps with a, let's say, circular sleeve will be placed above on this pole in the middle, and they will introduce the load to the pole in the middle, and this pole have to carry all loads and carry it down to the bottom. How you can set up this, I will show you in a live demo, and therefore I jump now to the program. So here I prepared open RFEM. With this program I will model this spiral staircase. Of course, we have to give this child a name, so spiral staircase let's say version 1. With a type of model, of course, this is a 3D model because we carry the loads around about the pole. So I use a type of model 3D. As task, what I want to solve in this model, I activate here the design add-on stress-strain analysis, what is taking over the calculation of stresses according to the internal forces and comparing it with the, let's say, limit stress of the assigned material. How this could be done and how it's, let's say, connected to the full model, I will show you in the following. Here, of course, you can decide for more actions. In this case, for example, I deactivate the load results because they are uninteresting here. They are mainly take care about, let's say, snow and wind, and this is no case for our stairway. In the next tab, we can select the standard of the load combination. So you see we have here a big list of available standards. I select here the Eurocode 0 with the CAN annex. Of course, you can select the country what you wish here. And in the final tab here, I check only that the z-axis is running downwards, that I can define as, let's say, we know it here, how to say that, what is common here, that you can define the self-weights with a positive sign. Later, we will use here the option representatives, but I will explain it in detail. So now let's jump in. And the program will offer us, let's say, a typical RFEM view. We get in the middle a graphical desktop. We get on the left a navigator, and on the bottom a table for defining inputs. And we directly begin with defining the pole in the middle. For this, I use a member with a member type beam and a section, let's say, from a circular hollow section, and a size I expect something about 180 millimeters. Therefore, I type in here according my table 177.8 what is the outer diameter, and the thickness let's say I search something with 10 millimeters, and you see as I define it here in this box, the program will reduce the cross-section library only to these elements what are fits. So I can select now, for example, from this European catalog, this cross-section here, and I can assign here a material. Here directly the first material fits. It's let's check it. It's a S235 material according to the Eurocode catalog, so everything fine, and I can read here, let's say, the properties, the stiffness properties and the limit stress properties. So this fits, and we can confirm this input and can jump into the 3D space to place this element. Because I expect that this pole have an initial dimension of, let's say, 4 meters, is starting from the origin. I place the first point in the origin, and let's say the upper point around about by 4 meters. So now I have the pole inside, so it looks pretty easy, and I realize, and what happens always, I have to connect it to my real dimensions according to my technical drawing, what I have here in on the desk. So if you have to modify something, you can always use the interaction of the navigator and the, let's say, table below. So for example, if we have to modify the nodes, you can pick directly the nodes, they will be highlighted, and I can write, okay, this should start 50 centimeters below because the foundation is more below the first stairway step. And on the top, you can also modify it if it's needed, so it's not 4 meters and minus 380.5. So this should show you only if you have special dimensions. You can change it in the table, but you can change it also by double-clicking the node and change it if it's needed. By the way, we just see here the material library with materials what are not needed, so you can select it here. It's the same for, let's say, the sections, everything what is not needed, you can remove. In the next point, we should start, let's say, thinking about how it's supported. So in my point of view, we support the pole hinged on the foundation, so I use a nodal support. And I use directly the first setting, what is supported with X, Y, Z, and with the rotation about Z. So we place this support here. In the next, we can think about how we can apply these prefabricated stair steps. And these stair steps, maybe only that you get a picture, it's this element here. And here we start, or let's say we define a level where we want to place it. And for this, I use my working plane, and it's, let's say, 8.5 centimeters above this point. How you can, so I want to open the topic, how you can move your working plane 8.5 centimeters upwards. For this, I recommend you to define a node and write here minus 8.5 centimeters. I get this node here in structure, and with this moving function, I can change the origin of this working plane. Here we can rotate it. Now you see it's on the XY plane, and everything what I, let's say, put in now is placed on this plane. So when I specify now the inner and the outer radius of this step, I know it's done on this plane. So I use here a circle function, pick the center, place my node, for example, here on such a grid point, and write maybe the inner radius, it's 9.7 centimeters. And the program generates me the line on the working plane. So you can check it by typing in, let's say, Y, and you see it's on this working plane. Now let's generate the, let's say, the outer radius. It's 1.45 centimeters away. So I use a line, and it should start here in the origin and should run here to 1.45 centimeters in X direction. If you, let's say, have nothing to pick on the end, so please see this dialog here. For example, you can specify option length and angle in work plane, and here I can write 145 centimeter length. So you see it's already on my cursor, it's in working plane, and when I pick here this function, I get directly a line with the length of 145 centimeters. Now, this is on the outer radius, this is the inner radius, and now we have to, let's say, design or construct this stair step by a rotation of this node. So I use this line here, rotate it by a copy by, let's say, minus 8.5 degree around C, and this is here the origin, and confirm this. And in the next, we rotate this line back to, let's say, 70 degree and confirm it. Now we receive with this action, let's say, the corner nodes of our stair step, and the, let's say, these lines are only here to get this node, so I can delete it. In the next part, we specify the outer boundary, or let's say the place of the boundary member of the stair step. So I pick this node, and now I want to pick here this quadrant point of this circle line. And you see the program don't offer me something. And maybe I lead you here to a new function in our program we inserted in the last weeks, months, such as status bar with snapping points, with modification commands, with clipping options. But here I'm interested in this point that I can find this quadrant points of such a circle. The same for the lower line here. And now I get slowly an idea of the size of this step. On the outer boundary, on the right side, we specify an arc from above these 3 nodes. And here, let's say, because we have this circular sleeve, I have only here such a half circle. So I cut, let's say, this circle with the definition nodes of the line and can delete here this left part and get only here this shape of this stair step. This middle line, let's say, we can generally delete, we don't need, but I have one, let's say, idea in background why I need it. Therefore, I change it a little bit. I take it, divide it by 2 nodes, and delete the right and the left part. Why? I explain you in let's say a few minutes later. I need it for controlling the coordinate system of the surface of the stair step. So, but at first, let's assign to these lines a stiffness. So I select it, lines, edit, and assign a member, and assign here a section. Let's make a new one, go to the library and say, let's say a sheet with 120 with a thickness of 5. And you see, when I write these figures, the catalog is reduced and I can select something, for example, this sheet here. Of course, because it's, let's say, orientated on the weak axis, so I rotate it by 90 degrees. And when I confirm it, you will see these lines get blue drawn. And when I visualize the cross section, you see I can, let's say, have applied here this member stiffness roundabout. Now in the next step, I have to, let's say, connect this stair step with the pole in the middle. And here I use a rigid beam. It's an element that have an infinite stiffness. And for me, I connected, let's say, also rigid to the pole because this circular hollow sleeve of this prefabricated step introducing the pole a bending moment, and I want to introduce also a bending moment. I need this modeling of this step only that I can carry the loads of the handrail through the step to the pole. So for me, it's only a let's say a option to carry loads with the right stiffness to the pole. So in the next step, we have to take care when I bring up a load on the stair step, because at the moment I have only members, how I can do this. And I plan to load these steps with a surface load, but right now I can look through, so I cannot apply a surface load. So I introduce in this boundary a surface and a special surface, because it's not a surface with a stiffness, and it's only a surface what has the job to suction a load and to distribute it to the neighbors. So a load transfer surface, we say to it. And for this, I, let's say, select these boundary lines. And now you see we have here an element inside. This element have, let's say, an axis system. So surface, axis system, you see here. And if I go into the properties, I can say, okay, how should the load transfer between the axis done? And I specify, okay, please distribute loads between the short sides. So between this and this, so between y-axis. So let's specify that this surface have a specific axis. So I control now the axis is X is always parallel to my controlling line what I prepared. At the moment, the question could appear, why he doing this? Because X is already running in this direction. That's clear. But imagine we want to rotate this step around the pole so it will move. So I fix it with this option. In the next step, I say, please distribute the loads about the y-axis. So in this direction, only on this let's say supporting elements. And further, I specify this surface have a weight for the self-weight load case. So let's say 0.2, 20 kilos. I apply. Now, so far, so good. We have now modeled a stair step, like a cake segment, what we can now in the next step copy and rotate around the pole. Of course, what we should not forget, we have also a handrail. So let's add directly a handrail width. So I select this node, copy, create here a copy element. I copy it up with -100 centimeters and directly create from between the copied node, so origin, copied node, a new member where I say I use a circular hollow section, a new section here from this library, and it should have a dimension of 50 multiplied with 2, maybe here with 2.5 millimeters from this steel, and confirm it. Rotation at the moment not important because we assign it later. And on the left side we do it almost similar. So I copied also up with -17 centimeters. It's a stair step high one time by using also this member, and in the next instance we say -100 and without step-link, so only a node here. Now we make to this vertical handrail poles also a horizontal handrail. I connect these two nodes. Now you can imagine if I rotate and copy it, it will connect it. The only thing what I have to take care of with these actions or with these planned actions about the coordinate systems. Here for loading, maybe for later loading. So I go here, member axis systems, and you will see maybe here is the axis running in this direction, here horizontal. So this is not really nice. So I select both members, edit, and go here to section, use here a help node, and define that this XC plane is showing to, let's say, the neighbor node on this side. This means now the XC plane is rotating so long until it covers this node. The same for the top member. Now for this we do the same. Help node, XC, and we use the node on the opposite side. So now I would say this stair step is modeled and we can start rotating. But for me, this is a fixed component. It's a prefabricated component what I can replace and can play with. So I want to show you today a new modeling style. I want to show you how you can work with blocks. Therefore, I select this stuff here and save it as block. This I ignore because stress strain is here not relevant, and give here a name. So let's say stair step. No. Maybe with capital. So, and I specify please save this below others, category other, general. Then I find it later. Now I confirm this setting. The program is thinking a while and storing it in database, and now it's finished. In this situation, I can delete it now. I don't need it anymore, but I open the block library and I search it. It was a stair step, and you see I find it here. I see a 3D picture, and with double click I can, let's say, take it over, but with a, let's say, a transfer menu which specify where it's placed in space, do we have a rotation, whatever. I confirm it, and now we have the same step here, but if I draw my mouse cursor around, you see such a box, a bounding box around. It's now a block. This stuff is now inserted in the program as special object, as block, what is connected, and this means it have also these coordinates. You see, you get now such logs. It's connected to this block step, a model block, what I can modify later. And this allows me now also to select it here in the navigator and to say, please copy this block 16 times minus 17 centimeters upwards without step links. Yes, and I confirm this. Now the program is not only copying members and nodes and cross sections, then the program is copying a model in model 16 times. So this eats a little bit of the performance, but you get some advantages later if you want to change something and so on. And this change I will show you when it's needed. So not directly during modeling, but when you go into design, it makes an effect if you can change it for one block in all blocks. So let's wait until he's finished. Now, oh, nice picture. All steps above, you don't see something, but the lucky situation is we have every stair step separately here in this menu. So I can jump in and can now specify the position of this block in space of the model. So the first step fit already, the others not. So here I specify here a direction. Open the menu and type in 1 degree. The question could appear, why he writing now 1 degree? The point is, I want now to change the angle for every step separately. And if he only finds 0 in his definition, he will directly deactivate this option, but I don't want to change the menu continuously. So I use this trick. And now we go to the second step and say, okay, we have a rotation of 70 degrees. And for the next step, we have, let's say, 2 times of 70. So I have to calculate it. And of course, I don't write it down, but if I don't know it, I write it what I want to calculate. So for example, 2 times 17. The same for this situation, 3 times 17. And now I jump through all, so let's say 4 times. 5. 6. This could appear like a little boring job, but let's say I inspired also our programmer already to make a moving rotation function, but at the moment I haven't. And I also want to show you how you can solve it in reality, even if you don't have a special function for it. So. And now 12 13 times 14 times 16 and the last one. Now it's done. And let's check if everything is right. So I confirm the dialog. And you see the upper one I forgot, so this last one I have to check. It was, let's say, 15 times and the last out here is again 1 and this is 16 times. Now oh, I have to check because why are there on the bottom? These last two. Oh, I changed it in the wrong. Sorry. Again a rotation. Now I have to change it in this menu, not here. So this was my fault. Okay. And the last one was 16 multiplied. Now everything fits. You see, we used now these block elements by producing the full spiral stair way. This visualization fits also, and the connection between the pole is also done. In the next step, we have to take care how we can connect the upper level connecting to the, let's say, concrete structure. For this, I expect this last stair step. So this one here will look a little bit different. I only use the placement. So I go here and explode it. And I get here, let's say, now red node instead of these blue nodes, what are generated. And I can delete what is not needed. So for example, this stuff is not needed, we can delete, but the fixation with the sleeve remains. We only model now, let's say, here we use these geometries to model this level. So I copy these nodes, copy one time into X, maybe with, because we don't know the dimension exactly, with 50 centimeters, and creating a line from it. And you see now we receive this, let's say, level geometry, and I can place now both nodes with the dimension of 145 centimeters. And here when we get a top view from top, you see they are ending directly on this place here, and these nodes we connect now. So I use here both nodes and have now a geometry of this level. And these members, let's say these lines are members, it's a L section, so I assign here a L cross section by using the library, going to the library, and it should be a, let's say, a L section of 150 multiplied with 100 and a thickness of 10, and from this steel. And now we can remove this rotation, and these lines get blue. you see, maybe this front member we can change also to the same section. It should be here, this L section. But the flange should show inside, so we take both and reverse orientation. And now it fits almost. We only have to make it a little bit more stable. So I insert here a beam, truss beam, what only can take over tension forces, and assign here a solid bar, a round solid bar, maybe with a diameter of 20 millimeters. And here I make only a cross that it, let's say, it's stiff enough to carry the upper part of this pole. So now we have to, let's say, take care about the connection to the massive structure on the right side. So I imagine I want to support this beam maybe 20 centimeters from the corner. So I double click this member, go to nodes on member, and right here, please use absolute dimensions and say please on the start 20 centimeters and on the end also 20 centimeters. And you will see you get two nodes with a distance 20 centimeters on the right and left side. And here we can place now a support. So on the first side near pole, we make a fixed support, and on the right side, we make a new support type, what we open in Y direction. So I open this degree of freedom and place this support here near this node. Now, the structure is already finished. The only part what is missing is the handrail on top, and here, if I place a load, I can look through. It cannot cover a load, so we have to insert here a surface. And in this case, because the stiffness is deciding which part is going to pole and to the supports, I use again a load transfer surface, but with the type isotropic finite element analysis. Of course, with a weight of 0.2 kilonewton per square meter. And if I place this into this structure, I know now when I run analysis and there's a load on this surface, it will calculate it in a submodel, only this surface with all boundary elements, and take over the line support forces on these boundaries as new loads in the structure. Now let's finalize it here to our, let's say, handrail. So I take these nodes by drag and drop and copy it upwards and place here now a hinged handrail. So let's use here a beam element with a hinge. A section is here our, let's say, circular hollow section with now rotation, and the hinge should used on the begin because it's fixed afterwards, so it should not introduce a bending moment. And yeah, let's place it here from here to here, and the same from here to here, and fix it on the wall. And for this we take a nodal support, a new type what is fixed against rotation about X, and C is free, and about these two nodes. Now we almost finished. The only thing what is missing is, for example, the coordinate system arrangement for members. Let's say I know the handrail coordinate system I aligned in the stair step already. The only point is missing that all is showing to the inner side, so this will be rotated also to the inner side by 180 degree. Now, Now we finished the part with the modeling. I know it was a little bit exhausting, but I planned this modeling step to show you how you can work with the program and which features are existing to solve such a structure. In the next step, we want to change to the loading. What means self-weight load case should act. So let's check it if we did everything right. For me, this is the best plausibility control. So I run analysis. You see this loading process. This is the sub-modeling process of this level, what I used here. And then for the next calculation, he used the support forces of this level as member loads on the structure. And you see, we get the equilibrium, we get also deflection curve already. Of course, you can visualize the deflection on the members more in a better way, and you see also weak point of the stair step. But for me, deflections are, let's say, smaller than 1 millimeter, so everything seems fine so far. We did first modeling right and can now go ahead with loading. And for this, I create the load case or two load cases. So one is a live load case, live load vertical, and the another is live load horizontal on the railway. For this, I apply load. So for the vertical part, I apply 5 kilonewton per square meter. And this is now pretty easy with this, let's say, load transfer surfaces, because I use a surface load, type in 5 in Z direction, and draw only a window about the full structure. And you see, the program is applying the load on the structure, and this 5 kilonewton will be distributed to the member roundabout, and I don't have to take care now. The same for the horizontal. So here I only have to select the member. So I use a member load. Let's use, for example, here into local direction, in Y direction, minus 1 kilonewton per meter. And here I pick, so if you don't want to see these boundary boxes, you can go into the display navigator and can say, okay, this bounding box should be deactivated. Then, oh, this is a wrong member. Now let's use all these members. Nope. Next time I will use a separate cross sections and I can select it in one step. And now we confirm it and get this load directly horizontally three-dimensional placed on this structure. And this is, let's say, a time saver for it if you have all coordinate systems already aligned and so on. So now we specified there could exist more loads, snow, wind, whatever, but this is not the point of this demo now. I only want to show you, okay, you can create different load types. The program is, let's say, directly combining all possible ULS and SLS combinations, but I want to show you a little bit more. We have these load cases. The program creates these, let's say, actions automatically, where it places these live loads with simultaneous setting. Then it has some, let's say, rules from the standard, from the 0.0. And for this demo now, I only want to have ultimate limit state. So the others I delete. And I want to design this design situation what is acting according this law for stress strain analysis. So if this design situation checks this stress analysis topic, the program knows, oh, I have to calculate the stress check for these members with this add-on. So if it's not checked, he say, no, I only do structure calculation. So this is the decider here. And in the bottom, you can decide how should the calculation or the combination done according geometrical nonlinearity or only linear without imperfection. Then you select it here. And this means if you jump to the next tab, you get the actions combined and finally the load combinations combined according linear theory with all gamma factors. And now we are ready to do a stress check. And this was everything what we have to do, not more. So I do now only calculate all. And this task, what we defined in the first seconds of this demo to activate in base data stress strain analysis is now considered. So the program is preparing these loads. Now this is the loading process of the transfer surface. Now it calculates the single load situations, the static analysis. You can read it here by SA. And after it's finished, he do a stress check. And here we get a picture of deflection, but where we are interested in, you have to know we have stresses in every single load combination. Yeah, you can visualize it here. For example, the normal stress you can activate here, and you get here a picture of this normal stress of this combination, It will be visualized directly on the cross section, but it's boring to check every individual. So therefore, we interested always in this stress check, what, let's say, makes an envelope of everything. Of course, this drawing of a multicolor picture on the cross section is difficult, but we visualize it then with such a diagram. So the program detects, so most important information here on the bottom, we have a maximum stress of 203 megapascal. Here you get a picture of the normal stress, of the shear stress, of the equivalent mesostress, or let's say compared to the allowed limit stress. So you get the utilization of around about 90%. No? This stuff is now, let's say, also in the table below. And in the table below, you get at first from the stress strain analysis overview. You see he had some issue with members. Member type is not designable. The question could appear, what is this? If you select it, the program will select this amount of objects in the graphics, and you see, it's this rigid member I can't design. And if you select the surfaces, deactivate for calculation surface, it's this transfer surface. Yeah, it could not be designed because we have no properties for it. But if you go here to stresses on members, you see, you get now a result by different sheets, stresses by design situation. We have only one, so you get here the biggest stresses for this design situation. Per loading, we have 4 load situations, so you get these stresses, the biggest result per load situation you applied. Per material, it's many because we have many materials, because there's many steps what we copied. This we will solve in the next steps, but so it's at the moment not so optimal. By sections the same. By member, you see we have how many? 142 members, so 142 rows. Pretty boring. Imagine you have to document it and make a document from it. So what we can do is we jump now again to base data and make a grouping. And the grouping could be done with the member representatives. If I activate it, the program will delete the result, of course. But what happened? It happened now that I get here member representatives, and you see it's again 107 representatives, so nothing good. And these representatives is, let's say, always a group of elements what means what they have the same materials, the same sections, the same line types, the same member types, the same lengths, and all properties what I defined. But it's 100, how much? 7. So what can we do? And this is exactly the point where we should think about the mother-child logic in blocks. So I jump again to the blocks and say, hey, we have 16 similar blocks. Can't we say 2 until 16 are, let's say, ruled by block 1? And in block 1, I can specify, please use for all sections material 1. For section 1, let's say section 2, and for the circular hollow section, let's use the last one, so this one. If I confirm it, the program will sum up everything and our representatives melt down to 16 positions. What happened now? Now the program found elements what belongs together. So we have one position, the pole in the middle. You see what is highlighted. We have one position, maybe the in front border of the steps, the back border, the outer, the rigid members, the, let's say, vertical handrail poles, these step poles, the handrail, these L sections, this bracing, and maybe here this handrail with individual length. So we have 16 unique positions now. And if we give the stress strain check not the job to design all members and surface also in unaddressing and only representatives, we get in the design finally 16 positions what is nice to read for your clients. So you see, oh, okay, all poles of handrail, you see all stairway steps, whatever. So you have a clear grouping of elements and you design only 16 positions. And let's see what happens. So we calculate the load situations again because we reassigned many cross sections. And now we get in the result stresses on representatives, stresses by representatives, a really nice table. Let's say with 16 rows. Here you see, okay, which member numbers belong to which representatives and what is the biggest result of it. And this is a really good table to document. So if you have now to make a documentation, you can say, oh, let's make a printout report. In the printout report, I want to see all basic data, material section notes, blocks. We want to see type for nodal supports is okay, line supports I haven't, hinges is okay, surfaces not, we don't need, load cases is okay, load combinations also maybe with a reduced description, loads, guide objects I don't need, part lists I don't need, static analysis setting only summary, stress analysis we say okay, cross sections and material already documented on the top, so only show results, and as results we take a table, stresses on member representatives, so what we just saw, and a design overview is not needed. So let's create a document from it. So you see I only checked a few options without more work, and you get a full document created. Where it is? Here, it's coming. So you get a document with a header, with a chapter description, with a preview model, with a content, description of cross sections, notes, lines, members, what is here, surface descriptions. So all data what we feed it into the model, a summary of loading with the biggest deflections, and finally stresses on member representatives by member representative tables. So this is 16 rows with the biggest results. Of course, this is pure, let's say, table stuff, but you can enrich it now with pictures also. So we can take our model and can say, please show me, so the program automatically generates representatives here. Show me first representatives on model. On this results, we see this result, and no, why we don't see it? What is wrong? Beam 1 again. This is object now. Now you see the utilization on this curve. Of course, we can use here also member visualization results without diagram. You see here such a multicolor gradient with the biggest utilization in the middle. And with this information, we can now printing pictures. Yeah, we say now print this picture, let's say window filling, with a high of 50% of the page into the report. And okay. Then you can jump to the next and can say next representatives. Let's say right border. Maybe you can sum it up with the back border and with the lateral border, and maybe this we can print from the top view. It's isometric better, and make a picture and go. Now go to the next pictures. It was maybe these rigid beams are uninteresting. This handrail pose, print a picture. So I can go through all and can, let's say, make a queue of pictures into the report. Of course, I don't want to show everything, but I want to inspire you how you can do it. And this is connected to this table, and your reader of the document understands it. So this is the way of documentation, what you can do. Of course, when we see now our structure and see, okay, biggest utilization is here almost 90%, a question could arise, this is only stress check. What is with, let's say, buckling, stability and such things? Yes, I agree. You should think also about such things. And when I check now the normal axis forces of such a structure, you will see, okay, we have up to 73 kilonewton pressure in one element. If you check it, you see it's mainly this pole in the middle. And I calculated the eigenvalues, and it's let's say it have buckling values bigger than 10, so it's not a problem. But to check it, I can offer the structure stability program to check the eigenvalues, or to offer or to use still design program. So if it's needed to make a further check, the program offers you to activate it. We can say, okay, please make a still check. And we say, okay, for this vertical column, when we watch it from the lateral side, so maybe in this direction, you see it's maybe here hinged placed, and this is let's say fix it here on this place also more or less horizontal. So I use maybe a pendulum column idea between these two situations. I place a node on this member. So I say this is a node on member. Then of course program wants to delete mesh, and now I can pick this member here, go to design types, go to effective length, say okay, please check buckling about both axes, torsional buckling, lateral torsional buckling. I'm not afraid of because it's a close cross section, but it should get properties from this element. You see we have a start, an inner and an end node. The first node is on the bottom, so the second is here. So here we fix it horizontally, and on the top we assume nothing. So, and this setting we place or we give to the steel design. And now we open the steel design. Of course, we can calculate everything, but let's check only this member in the middle, what have the highest normal axis force. And if we run analysis, we hope that we will get a approval. And here we run again through the full process about loading, load envelope for the load transfer surfaces, and now the load combinations 1, 2, 4. And you see now we get a utilization curve about this member what we checked. The biggest result is almost 40%, so the plausibility is also okay. This top level is not loaded much, then only here at this top. And if we go to the checks per, let's say, per member, you will see he did a lot of cross-section proofs, so compression, torsion, shear, and so on. But this is covered with the stress check, I would say. And stability, we have lecture buckling about Y and Z axis, and bending and buckling according to 6.33 check, and we about 40%. Of course, you can see it here in detail how this check is made. So if it's needed, you can open the hand calculation here in this detail window. But for checking the structure, this is quite easy. And I think, well, this was my intention to show you, and this is, I want to close also, how you can take such models and solve it with RFEM quite efficiently with this block technology and using the different add-ons. And with this, I give back to Andreas.
Yeah, okay. I thank Andreas for the presentation. Before I show you the website where you can find the recording and the model, I would like to give you a hint. You can book your free online appointment, just for example, product demonstration or something like that. If you want that one of our employees give you an introduction to any add-on or in the program, yeah, just contact our sales team. You can scan the QR code or click that link here in the PowerPoint. You can also download PowerPoint from our website. And I would like to show you the website. Most of you know our website, dlubal.com. And under news and events, here in the middle, you find the webinars. And yeah, those are the webinars in the next year. We start with the FAQ webinar that we usually present every month or 5 weekends also. Then the Grasshopper interface we would like to introduce with that webinar. Then I will present that webinar, news in RFEM 6 and RSTAP 9. I present new features of the last year, new add-ons, new features in the add-ons and in the program, and so on. Then The geotechnical analysis webinar follows. Timber design, floor design. The next FAQ webinar. And yeah, that's today's webinar. I click on it. In the next days, you will get an email with a direct link to that page. And then you will find the recording in the middle instead of that video. You can already download the presentation slides and the model. Okay, that should be also all from my side. Thank you for your attention. Thanks to Andreas for this nice presentation. Thanks to Lucas for the support by answering the questions. Yeah, I wish all a Merry Christmas and a Happy New Year. I hope we meet each other next year by another webinar. Okay, bye-bye. Stay healthy.